Okay, so today is another lecture about graph algorithms. Last time we were focusing on sort of trees and spanning sets and connectivity. Today is also going to be a connectivity themed class, although the emphasis will be in directed graphs. And some of this meta theme of having kind of two problems going on at once will also play a role. So, okay. So here's sort of the, very, high-level question that we often ask about networks and graphs. So I give you some kind of graph. Here we're just looking at unweighted graphs. At some level, the weighted analogs will be discussed next class. And in general, we have 2 points S and T, and I kind of want to know how well S is connected to T. That's just a very natural question to ask. But here the word connected, or in particular, well-connected, is not really well defined. I mean, there's many possible ways to interpret it, and maybe for different applications, different things are called for. So, but let me first point out some examples. I guess this is sort of ironic given the current development in news. Well, a lot of the stuff we'll discuss today was actually developed sort of World War II, post-World War II, early Cold War, kind of when operations research is picking up steam. So they're analyzing, I guess in this case, this is railroad networks, but it could be electrical networks or something else. Here they're analyzing the physical infrastructure of Eastern Europe, and they're actually trying to find weak points in the network. And it's a little hard to probably see on the projector, but there is this part that's circled. Sorry. There is a part of the graph that's circled here. Okay. For some reason. And then there's these words, the bottleneck. So you could see them analyzing and try to find, I guess, what they decide is the bottleneck of the network, whatever that means. Okay, this is actually a relatively small graph compared to modern examples. I've mentioned CPUs many times. Here then would be a picture. But the point is that CPUs have many components and many connections. And you want not only the connections to generally be small so that the messages don't take a long time, but you actually want the CPUs to be very robust. So CPUs actually have many tiny failing parts, but there's actually backup plans built in. So this makes things much more economic to build as well, because you don't have to be perfect. Right? There's some fault tolerance built into these networks you build, so that if one, microscopic electric wire fails on you, there's backups. Okay. Here's a picture that you guys have all seen. This is the picture that Facebook put out like 13 years ago, so it's been updated since. But of course, they've sort of plotted all their users geographically and drawn lines connecting pairs. Right? And there's always these games like 5 Degrees of Kevin Bacon or whatever. How many friendship hops are you away from someone else? So I put S here in roughly Indiana. Actually, that looks a little too much in the middle. That was supposed to be Lafayette. Here is my grandmother in Japan or something, who doesn't use Facebook, so probably isn't on this map, but nonetheless. Yeah. Well, of course, Facebook is interested in understanding, when they analyze a graph, they're analyzing the community structure and trying to understand the implications thereof. You could see the effect of the Chinese firewall in just a dark part of the map. Okay. Another example for analyzing graphs is the World Wide Web. This is something I pulled from a Wikipedia article. But, at some level, each of these labels represents a website. And these lines sort of represent links between websites. Okay. And analyzing the link structure of the World Wide Web can actually tell you a lot about which websites are more related to others. It can also tell you a lot about which websites are maybe better than others, right? A good website will have many other websites linking to it, and so forth. Okay, so that would be another example of a large graph, and at some level, understanding how 2 points are related, how they're connected in the graph, is of tremendous interest. Okay. All right, so I only vaguely said, okay, S and T, how well are they connected? There's a lot of different ways to actually formulate that question, some of which we've already asked. Right, so this is one we did early on, which is just whether or not you can go from S to T. Right? This is just, is there a connection? And we resolve this using depth-first search. In fact, at some level, we can take strongly connected components and figure out a lot about all the connections, or yes or no, all at once. Okay. Fine. Here is another question that might be reasonable, which is, how many paths are there from S to T? How many paths are there from S to T? So this question is much harder because for starters the answer might be very, very, very large. So if you're going to literally count them, you might just have to spend exponential time right off. There can be exponentially many paths from S to T, although I believe that sitting in the exercises, there's two special cases that you can do. One is, if the graph was a DAG, how many paths are there from S to T? Okay, you might try that. And the other is, how many shortest paths are there from S to T? But the trick is just that the shortest paths form a DAG, or the edges in shortest paths. All right, that's only another question, but something someone might ask. Another question might be, it's a little more tractable. How many ways can I get from S to T using k edges for some parameter k? Maybe I'm not really interested in really, really long walks because that doesn't mean as much for whatever application. I'm only interested in, say, I'm in a social network, how many people are 2 hops away? Or can I get from point A to point B in 5 hops? So this question, maybe I'll take a raise of hands. So the question is, how many k-edge walks are there from point A to point B? And let's say k is a small number, like 10 or something. Okay. So if it was 10, you have 2 choices. So you're counting. It could be a large number. But so who thinks it'll be there's a polynomial time algorithm for 10? And who thinks that there isn't? So let me do the usual P or NP. We haven't done this in a while. All right, who thinks we can solve this problem in polynomial time? I want to figure out how many ways I can get from point A to point B using 10 edges. Exactly 10. Okay, most. I didn't ask who's not going to vote. Oh well. And who doesn't think? Who thinks this will turn out to be hard? Okay, all right, so 20% not voting. Yeah, at some level you should be able to take Bellman-Ford style stuff and kind of carry with you how many ways you got from point A to point B and get something very similar. Okay? Or maybe another way is to just make k layers and then do the DAG thing we had just discussed. Okay, fine, that's another question. Here's another question we had worked on. What is the length of the shortest path from S to T? We know how to do this. This is breadth-first search. This is Dijkstra's algorithm. Right? But there may be lots of applications where if something's really close, we understand them to be very similar. Okay. This we already discussed. How many shortest S to T paths? Okay, fine. Okay. Another question. If I started at S and I took a random walk from S, So what does that mean? Each step I start here and I just choose one of the edges at random. Oh, okay, maybe I go here, right? And I flip a coin, I either go up or down. It comes out tails, so I go down, right? And I'm here, I flip a coin, maybe you go up. Okay, so you can do a random walk. And maybe or maybe not you'll get to T after some number of steps. Okay? And then maybe when you get to T, you said, oh, I took 100 steps already, or 101 steps already. Maybe you never get to T. But it's reasonable to ask, if you simulate this random experiment, gazillion times, what's the average going to be? What's the average number of steps to get from S to T? Okay. This might seem unnecessarily technical compared to some of the stuff we've done, but this is how PageRank works. Or it's very similar to PageRank. Okay, they model the internet probabilistically, and they study random walks from point A to point B. Okay, here's another question. What is the maximum number of edge disjoint paths from S to T? Okay, so before there's this issue of like how many paths there are at all, maybe that's exponentially large, that's intimidating. But if they're edge disjoint, so two paths can't use the same edge, now the total number is much more limited. Right, so it's not this issue of, I can't count to a really large number. But this is also a very natural question to ask. What is the maximum number of edge disjoint S to T paths? Okay. So I thought I would ask for this graph, what is the maximum number of edge disjoint paths from S to T? So you have to find as many paths as you can from S to T, and your choice of paths cannot share any edges. Yeah. All right, 2. Okay, so I'll start here, and you can just direct me where to go for one path at a time.
The top one.
Okay, up. Up again. Okay, down to the right. Up. Oh, you can keep going, right? Or you? Suppose whenever I forget to draw an edge, suppose you can use both directions, because I think I've forgotten a couple places.
If you go back to the before you did the down, up again.
Oh.
And then down 2.
Okay. All right, so that's one. Let's do the other one. So probably going that way, and then down, up, down again, up to, here. Okay. All right, and it seemed like at a high level your strategy was to go high and go low and hope they don't intersect each other. I'll only point out that sometimes in the real graphs we don't have a clear sense of down and up. Okay, but this works. I think this is trickier than some of the problems we've solved before. We even ended up reusing the same vertex twice, which is allowed in this problem. Okay, but anyway, so, but these are two paths from S to T that are edge disjoint. Okay. All right. Did anyone do better than 2? Yeah.
You can't, because there's only 2.
Okay. This is very good. Not only could you not do better than 2, but you're probably happy at 2, because you might have noticed that at the beginning at S, there's only 2 ways to leave S, so you definitely can't do better than 2. So you also identified some kind of bottleneck that made it clear to you that you had the optimum solution. Okay? And in general, this is a rare thing. The idea of, okay, I have something, it seems pretty good, but can I certify it's the best possible answer? But here you can, because you know that 2 is the max, because that's how many edges leave S. Okay. All right, this example seemed easy. It's not obvious if we can get a good algorithm. So I'll take a vote. Starting with who's not voting. Okay. All right. Who thinks we'll be able to come up with an algorithm? Okay, I'll say like 55%. And who doesn't think we'll come up with much of an algorithm? Okay. That also seems like 55%. Okay. Good. Very enthusiastic vote. Okay. Great. Let me give, we've done a lot of max questions. Let me give the min one. Suppose, and this is maybe the question that the military was looking at. But suppose now I want to delete edges so that S can no longer get to T. And I want to delete as few edges as possible, because each one is expensive to get rid of. Okay, same graph. What is the minimum number of edges I need to delete to make sure I can't get from S to T? Yeah. 2, give me, there's probably multiple choices, so give me an example of 2, I guess.
I was thinking if it's simply to disconnect S from T, take all the out edges from S.
Okay, all the out edges from S. Simple enough. I mean, S2. Okay, yeah, I'm being an annoying teacher. Did anyone do better than 2? Can we remove one edge? Does anyone can anyone argue that besides the fact that we can't find one edge to remove, but more compactly, or for lazy people, how can I justify that 2 is the right answer? Yeah.
Because we just found out that there's 2 edge disjoint, meaning we don't share any edges, there's 2 paths.
Okay, so we just showed that there's 2 different paths not using any of the same edges from S to T. So whatever our deletion solution is, it has to take at least one edge from each of those paths. So we already knew that this minimum size ST cut, as it's called, because you're sort of cutting them off, had to be at least the number of edges, edge disjoint paths from S to T. Okay. So again, you have this very nice thing where you can mutually certify one another. Okay. Which, again, maybe for this example is not as compelling, but for a much bigger graph, and it's not obvious if you can improve your solution or not, it's very, very important to be able to get a certificate to know that you have the right answer. Okay, I'll take the same vote again. Starting with who's not going to vote. This is for the cut problem. Minimum ST cut. Okay, same people. Consistency is good. All right, who thinks we'll have an algorithm in polynomial time? Okay, I think that's less than 50%. I'll put 45. And who thinks we won't have an algorithm? Put that at 55. Okay, so that's great. We are going to focus on those last 2 questions, the maximum number of edge disjoint paths and the minimum number of edges to delete, disconnect S from T. And I'm glad we're very close to 50-50, so at least half of you will be surprised. Okay, so anyway, those are all the questions that I went through. I could have come up with more. Okay. The only point being, there's lots of questions one can ask. Okay. We're going to focus on these last 2 questions today. Okay. We're also going to talk about how they're connected. Okay, so that question of finding the maximum number of edge disjoint paths. Now, I started ranting last class about packing and covering problems. this will be another example of a packing problem. Okay? What's the idea? I'm trying to take as many paths as possible, but each path sort of uses up all the edges that's in the path. Okay, so I can kind of think of packing paths into the edges of the graph and trying to pack as many as possible. I have some limiting constraints. Namely, I can't use an edge more than once. Okay, so this is a generic example of a packing problem. And again, the object being packed is paths. You have many choices of paths, but the limited constraints are the edges. Okay, so if we're using pack as a verb, the path is getting packed into the edges. Okay. All right. This doesn't fit at all. Okay. Okay. And then the other question, deleting the minimum number of edges so I can no longer get from S to T. So such an edge set is called an S to T cut. It cuts off S from T. So this problem is sometimes called the minimum ST cut. Okay. You can also do versions with cost on edges. We won't discuss that today. We'll discuss that next time. Okay. But this would be an example of a covering problem, so to speak. The way to think of it is like this. So I want to take the minimum set of edges so there's no more paths left going from S to T. So another way to phrase that is to take a set of edges so that for every S to T path, you're taking at least one of those edges. Okay. So the edges are covering paths. I need to take at least one edge from every path. There may be exponentially many paths. Doesn't mean you have to take exponentially many edges. You just have to take at least one edge from every S to T path. Okay, so edges cover paths in this case. Okay, so we can write this as, okay, I want to get the minimum set of edges that covers all the paths from S to T. Okay. And so the theme I'm trying to emphasize here, that sort of continues something from Tuesday, is that we have this this duality of kind of two related problems. They're sort of symmetric. On one hand, we have these paths that are being packed into each edge in the path. Okay. And we also have each edge in the other problem covering each path. Okay. I think that this is all should be pretty intuitive and at some level was already implicit in the answers and the questions in the interactive part a few minutes ago. This is just putting some vocabulary on it that also extend to other problems. Okay, so alright, so here's a lemma that we've essentially already discussed. Okay, relating those two problems. For any graph, the maximum number of edge disjoint S to T paths is bounded above by the minimum number of edges in any S to T cut. Okay. And at some level, for us, that was just those first two edges at the beginning giving a cut that certified our solution of 2. That would be the concrete example. Okay. But and we'll do the lemma again just to be sure. But one thing to keep an eye out for is that the argument is really just going to use this kind of anti-symmetric packing and covering relation. The fact that one object packs into another and that object covers the first. Yeah?
Why is it not just equals? Why is it less than or equal?
So in our example, it was equals. It's not at all obvious that it should be equals, though, in general. Equals would be great, but the upper bound is easier to do. So once we get past this side, which is just that, oh, it must be less than equal, then we're going to move on to the actual question of equality, which would be ideal. Okay. All right, so this proof will be much, this is the short part of the class, and then we'll get into the complicated part. Okay. All right, so it's not such a big deal. Another way to say this is that for any packing of paths and any ST cut, the number of edges in the cut is at least the number of edges in the path packing. The number of paths in the path packing. Okay. So if you gave me a collection of S to T paths, okay, and we had some set of edges that we were removing, or something like that. Okay. All right, so what do we know? We know that since, and again, this should be intuitive, we're just formalizing our discussion. We know that each of our paths has to have at least one edge from this cut, because that's what cuts are. Okay. So for each path, let's choose one of the edges that are in the path and the cut. It's possible that the path goes through the cut multiple times. It doesn't have to be one, but it's at least one. Okay. All right, so one key point though is that the paths are edge disjoint. So whenever a path chooses some edge from the cut, those are different choices automatically. And now all that's left is some summations. So the number of paths in our packing is, I can write the number of paths as 1 per path. Okay. I know that every path has at least one edge from the cut. Okay, so if I took the intersection of the path, treating it as a set of edges, and I took the intersection with C, treating it as a set of edges, that's always at least one. Okay. And the great thing is that there's no overlaps in this set because the P's are disjoint. Okay, so they're all summing different parts of the set C. Okay, so you just end it like that. Okay, so again, we just do, 1 point per path. There's at least one edge from the cut in every path, so P and C is greater than or equal to 1. And then the fact that those sets in the sum are disjoint lets us kind of combine everything. Okay. There's no overlaps. Okay, simple enough. This is, I think, just putting in hieroglyphics what maybe was already apparent. Okay. But maybe one thing to point out is that I'm really only using this packing and covering relationship between the paths and the edges in the cut. Okay, once sort of that relationship was established, I'm not thinking that much about the graph. Okay. This is useful because there's lots of other packing and covering problems, and you always get one inequality for free, which is this inequality. Packing is less than equal to covering. All right, so let's move on to this algorithmic question, which was 55-55, if I remember. How do I compute the maximum number of edge disjoint paths from S to T? And can we do it? Okay. Does anyone want to propose an algorithm? Or explain their thinking when they solve this question? Yeah.
Using some sort of source path like Dijkstra's, but as you take edges from S to T, you remove them from the graph, and then you keep doing it until you take it from S to T anymore.
Okay. So I would call this a greedy algorithm. You could do shortest path. I'm not sure if I'm doing the shortest path, so forgive me. But it's still interesting if you just did any path. Okay, so there was one path from our solution earlier. And you might say, okay, I've already taken this. I don't want to reuse those edges, so let me delete. Oh no, not that. We're going in. Okay, right? Say, okay, I already used those edges. Let me rip that out of the graph. Let me use the remaining edges to find another path. Remember correctly, that's wrong, okay. Maybe like this. I'm a little bit confused. Oh, did I screw this up?
No, you got it down.
Oh, down, okay. Okay, I think it's a little different than our solution earlier, but okay, at least it works. But nonetheless, I find the next path. I rip out those edges. Yeah. Linear time for a computer is very fast, but for me it's boring. Okay. So we rip out those edges and I look for another path and say I can't find another path. Okay, so it's a very natural approach. I'll call it the greedy approach. Maybe finding a shorter path makes sense insofar you're not using as much edges. So we can also keep that in mind. Okay. Right, so so while there's a path from S to T, find one, rip it out, keep going. Okay? All right. Okay. So let me look at this very simple example. Okay? So this is just 4 vertices. There's one extra edge going down the middle. Let's say S and T are on the outside. So S is on the left. T is on the right. Okay. And I think we can all see that the answer is 2. I go up. I go down. Right? But, of course, if I had chosen for my first path something like this, right, I would have nothing left on the right, and I would halt after finding only one path. Okay, and this is like the world's simplest graph. Right? Now, one suggestion was, okay, what if we had done the shortest path? And it's true, the shortest path would figure out, okay, take 2, take 2. But how can I rig this graph so that the shortest path wouldn't work? The shortest path version wouldn't work. Yeah. Yeah, so heavy in this case means many edges, so to speak. So I'm going to take this bottom left edge, I'm going to split it up into many edges. At some level, it doesn't make the graph any more complicated, but it makes that direction much less appealing. And I could do the same thing up here. Okay. So in my counterexample, I've actually taken now the shortest path from S to T, and it led me astray. Okay. All right. Okay. What comes next? Okay, so that's good, that's bad. All right. Does anyone have any ideas besides the greedy algorithm? The next step is definitely hard to guess, but I thought it'd be interesting to ask. Yeah. Oh, maybe dynamic programming? Yeah, it's not clear. It's not clear how to frame it as dynamic programming, although it's always a good idea. maybe I should mention that, or maybe one way to relate though your suggestion, what is sort of the sub-problems we're working with. So I would say from the greedy point of view, our sub-problem is like, there's only a subgraph remaining. Now find the maximum flow remaining, which is just one more path at a time. Or the maximum number of edge disjoint paths, so to speak. In other words, once I take the top path, so maybe my original problem is find the maximum number of edge disjoint paths. And our logic is sort of like, okay, once I find this top one, let me delete all this, and here's my next sub-problem. Find the maximum number of edge disjoint paths and what's left. Okay. And the only issue is, here, in my counterexample, if I delete those edges I took, my sub-problem leaves no path left, so to speak. Okay, so, I don't know if that's helpful, but as far as the dynamic programming suggestion goes, I'll suggest that there's some issue with also identifying the right subproblem, because it seems like as soon as I deleted those edges forever, by taking that wrong path initially, I was never ever going to be able to recover the original graph. There's another issue of, if my subproblems are just subgraphs, there could be just tons of subproblems depending on which paths I've taken so far. I mean, exponentially many. Yeah.
What I do, I divide the graph into connected components in it, and then don't eliminate the component B.
Okay, can I divide the graph based on connected components? So in this example, there's actually no strongly connected components.
Just connected from S and connected to T. So you split it into two, and the two components are connected by two edges, so that's the maximum of two edges.
Well, yeah, I mean, we have to define what component means, but I'll point out in our simple graph that this is even a DAG. There's no cycles. And so as far as kind of components go, S can, yeah.
Could we use the lemma from earlier and see if removing a path or an edge from each of the paths that we found disconnects S from T as well?
Oh, okay. Sure. Okay. Can I be wary? Well, first, okay. Okay. Can I somehow use the previous lemma and try to avoid disconnecting S from T while still okay, so let me maybe give a more exaggerated example. So if I gave you a graph like this, which I'm basically ramping up the previous one, of course the solution is to send 4 paths across the middle. Okay. The worst case is to zigzag. Right? Then you only end up with 1. Now, as far as the suggestion of, hey, don't take a path if it just kills you right away. Right? So this one has a little bit more room to make mistakes. So if with my first choice I only did the zigzag once, it's already game over. I'm never going to get to 4. Because I used up 2 of the middle edges. And I don't really know that this is such a mistake from that point of view, because I haven't quite disconnected S to T yet. And it's not that obvious to a computer that those middle edges are so crucially important. For you, you're looking at a simple symmetric picture, so you can clearly see the solutions for and stuff like that. Alright, so the greedy algorithm doesn't seem to work, and simple variations like getting the shortest path seems not to work. Okay. Even on simple examples. Okay. Because at some level, the problem is that when I take that middle path, I leave nothing. I don't leave enough. Okay. Now, the greedy algorithm is extremely logical. I'm pretty sure people are actually using it for a long time, like in 60, 70 years ago, before they realized there's these. But anyways, they're also using like vacuum tubes, so they can be forgiven. Okay, so the logic is very clear. Ripping out paths is very safe. It's conservative. It makes sure we never reuse an edge. Okay? But it's also a little overly safe in the sense that once I ripped out those edges, it seemed hopeless. Okay? So we're going to question this premise. Is it really necessary to remove all the edges? Is there an alternative? Okay, so let me suggest this to build some intuition. So on the left, I've drawn two paths between the same set of four vertices. So that's the same four vertices. Okay. One path goes up, down, and then to the right. The other one goes down, up, and to the right. Okay. Now, if I combine these edge sets, we'd end up with one going up, one going down. Right, I'm sort of just adding all the edges together. Okay. Now the middle edge, I have one going up and I have one going down. So there's really kind of two directed edges there. Okay. But I can decompose this differently. Right? I can write this as this plus this plus this. Right? Okay, nothing special. I'm just taking a set of edges and splitting it up in two different ways. Okay. Well, what's the idea? These opposite edges, at some level, can cancel out. Right? I can take my two paths that are using opposite edges in the middle and sort of switch the beginning of one with the end of the other. Okay. So, in other words, here is, on the left, here is that path that we might have taken with our greedy algorithm that killed us. Right? And that graph, there was nothing left. There was nothing I could do. Okay? But at some level, I could sort of have found a path that looks more like this, knowing that I could sort of undo that middle edge by playing the game like this. Because on the right, I sort of have two paths that do make sense in the original graph. Okay? This might be a little vague at the moment. In other words, suppose after taking the wrong path, I had the foresight to sort of add in the middle edge in the opposite direction. And then, if I ran the algorithm for a second iteration, it would find this path. Okay? Now, at the moment, this seems like cheating, since we're not allowed to use the middle path going up. Originally, there's only an edge going down, and not an edge going up in the middle. But I do know that sort of it contains two paths, the edges I've selected. And at some level, these two can kind of cancel out. Okay, so let me make this more formal. Okay, so in general, so let's say that I had two edge disjoint paths. Okay, so the red would be one edge disjoint path. The purple would be another. Okay? And suppose they had an opposite pair of edges. So they both kind of, there's some edge where one goes forwards, one goes backwards. Okay? I know that I can always extract two subpaths. I'll draw it again. Heroes in green, right? So just in this simple example, right? So those were two paths that were kind of overlapping in opposite directions originally. And then from there, I can extract two paths that are completely edge disjoint and don't have any opposite edges. Right? The green is a subset of red union purple. That's the point. Except I'm not using any kind of opposite pairs simultaneously. And so what's of course the idea is that whenever I find that my path is using kind of opposite edges, right? So one's going down and one's going like this, I can take the beginning of one and then append the second half of the other and do that simultaneously for both. All right, so that's, I mean, there's not much, okay, so let's say that P uses E, an edge E, right? And that Q uses D, where D is in the opposite direction. Right, so Q is kind of coming in like, Q is coming in like that. Okay. I can always sort of get rid of this opposite pair of edges by, I'll call this P1 and P2. So P1, it goes P1, then E, then P2. And on the Q side, it'll go Q1, then D, then Q2. So Q1 and Q2 represent kind of parts of the path, right? And I can combine, sort of P1 with Q2 to get a path. And I can combine Q1 with P2 and get a path. Now Q1 starts at S and P2 ends at T, so you still have an ST path. P1 started at S and Q2 ended at T, so you still have an ST path. Except I've sort of gotten rid of that opposite pair of edges. Okay. Now, of course, there may be more than one opposite pair of edges. So, whatever. If there's 10, I'll first get rid of 1. Now there's 9. And then by induction, I handle 9. Basically, you just repeat until you get rid of all the opposite pairs. Yeah?
This still only works if you have like an opposite pair though, right?
Yes. So we haven't changed our algorithm yet, but we do now kind of know that I can handle opposite pairs. I can cancel them out. So now let's use that in an algorithm. Okay. So here then is the algorithm called the augmenting path algorithm. It's very similar to the greedy algorithm, but it's going to leverage this sort of canceling out trick. Okay, so let me first explain the algorithm. So it's very similar. Okay, so initially it's the same, right? While there's a path, take the path and remove all the edges from the graph. That's just like before. Okay? But now, I'm going to take that path and I'm going to add back all of the reversed edges. Because I kind of know that even if a subsequent path took it, I'll be able to deal with it. We'll formalize this. Okay? So I actually know that the opposite edges are now safe because I can uncross them later. Okay, so this is the key step. The key step is that we're going to add the reverse of all the edges we've taken to the graph. I have some pictures coming up. And then, now the path I took may be using edges that from a previous iteration were added. They were opposite edges, so to speak. So I might uncross the path I just took with the previously selected paths to get rid of those opposite edges. All right, so it's a greedy algorithm in some sense, except our subproblems, we have this residual graph that's being updated. Okay, so here then is an example. All right, so bad case. I choose the wrong path. Right? But what we're going to do is, yes, I'm going to delete those edges initially. But I'm going to add back the reverse. Okay, so, not sure the best way to. Okay, so I've already taken this yellow path. But it's not too messy. And I've now added back the reverse edges. Which, I don't know if you can tell, but there's now green arrows in the opposite directions. Okay. Now I'm going to look in this path. Okay, let me do something better. Okay. So so now we have this graph, and I'm going to look for a path in this one. Okay. So now I easily see that I can go like that. Right? Back in my mind, I know that I can deal with those middle edges and uncross them. Okay. In fact, you don't even literally have to uncross them. You can just add the reverse edge back and deal with all the uncrossing at the very end. It won't really change the number of paths. And if you're only interested in now putting a number of paths to get from S to T, you don't literally have to uncross them. You just have to remember how to update your residual graph. Knowing the math would have taken care of itself had you done it. Okay, so I'll duplicate this. Okay. And okay, so we'll update this residual graph, which means I'm going to add the backwards edges and delete the forward edges. Okay. And what color should I use? Okay. We actually end up with the original direction of the middle edge if I added the reverse. Alternatively, I could have literally uncrossed those paths and then I would have that middle edge back. Okay. But, okay, so I've added the reverse of the edges I used in purple. Okay. And now I can see that I can't get from left to right because all the edges are pointed towards the source, also away from the sink. Okay. So, with this residual graph trick, you do solve our very simple example. Okay? Alright. So that's the key idea, is this idea of realizing that you can kind of undo some of your past decisions. Okay? So even if at some level, the algorithm is not very selective about which path it took. So it's not like we had to do the shortest path or some other recipe for choosing your paths. It was the ability to kind of undo past mistakes. All right. Okay, so we want to prove that this algorithm works always, not just for vertex graphs that are DAGs. And we will need to also start discussing ST cuts and stuff as well. It's not obvious how to prove this thing works. It is true that this won't. Right now we do know that we'll compute a feasible path packing, that we're not cheating by adding these reverse edges, that you can uncross stuff. So you will produce a feasible solution. It is not at all clear that you'll get the optimum solution. Okay, so put our notes on the right. All right, so let's set up. Okay, so for the rest of this proof, I'm thinking of sort of dividing the graph into two parts. Okay, based on two sets of vertices, whatever the set of vertices. Okay. So S, it's really capital S, but I realize capital S looks just like lowercase s. So now it's S with a line underneath. So capital S represents some set of vertices that includes the source, and T is the remaining vertices and it includes the sink. Okay, so I'm just splitting the graph in half. Okay. Now the edges that go from capital S to capital T must be an ST cut. Because it's some set containing the source, all the edges leaving there, to some set containing the sink. So if I deleted all those edges, I can never get out of this set and into the other set. Not necessarily a minimum SD cut or anything like that, just a generic SD cut. Okay, so C represents an SD cut. Okay, so we're going to do a counting argument. Now, let's take any path from left to right. I need a different color. Okay, so let's say I took, just to make it interesting, this path did I go the wrong way? Okay, this is not a great path. Let me start over. Okay. I did think it would be more fun to go back and forth across the cut. Okay, there's a path. Okay. Now, one thing to point out is that no matter how I drew the path, I would have gone from green to red, red-orange, at least one more time than I've gone from red to green. Because I start in green, end in red. You probably would just go once. Our more obvious solutions just went across once. But just to make it interesting, I went back and forth, back and forth. But every time I come back, I still have to get back across, right? It's like crossing a river. To get to the other side, I have to go across the river ultimately one more time in the reverse. All right, so that much we know. That's simple enough. Now, every time I take a path from S to T, I add all the reverse edges. I delete those edges from the path, and I added all the reverse edges. Right? So in particular, if I'm focusing on the cut, in that picture I had two forward edges. I went from left to right twice, and I went back once. So if I add the reverse, I'll end up with one edge going from left to right, and two edges going from right to left. So if I updated the graph and I again colored it yellow when it's going from left to right, the number of yellow edges will go down by 1. The number of edges in the ST cut goes down by 1. So originally I had 2 going forwards, 1 going backwards. I flipped them around. That would leave 2 going backwards, 1 going forwards. So it's a net loss of 1 forward edge. So every time I take an S to T path, in the updated residual graph, the number of edges in that cut goes down by 1. Okay. Now, when the algorithm terminates, there's no path left from S to T. Okay. So, there's some set of vertices that S can reach. Okay? And then I can't go any further. In particular, I can't get to T. So there might be a bunch of edges going like this into S, but there's no edges leaving this green set. Okay? And then I have, whatever rest of the graph over there. Okay? So as I'm updating the residual graph, the algorithm ends when I can't get from S to T anymore. So there will be some green region that the source can get to, but then I'm going to hit that river I can't cross anymore, that cut. And then there's the rest of the graph. Okay. So in hindsight, suppose I had taken the part that reaches S, that S can reach, at the end, as that capital set S, and everyone else as the capital set T. Okay, so let's we'll retroactively kind of fit my first picture. So capital S is the set of vertices that are reachable from S in the residual graph at the end. T is everyone else. And C is will always denote the number of edges from capital S to capital T. So at the end, C is empty. There was no edges left to leave capital S and get the capital T. Okay. Now, every path I took started with an original set of edges and decreased it by 1. So there was some original. I want to reverse engineer how many edges were in C before anything started. Okay. So each path decreased the size of C by 1. At the end, there was no edges left in that set C. Okay. Now, each iteration might subtract 2 edges and add 1 edge, or something like that. But it was always a net loss of 1. So that tells us, what connection then do we have between the number of paths packed and the number of edges in C initially? Less than, bigger than, equal than? Yeah.
Would it just be equal?
It'll be equal. Because each one loses 1 edge at a time. And at the end it's empty. Okay, so we have equality. And initially C was an S to T cut. So this cut and that vertex split that appears at the end of the algorithm gives a certificate in the original graph that we got the right answer. Okay, so we had this original lemma, right? That the maximum number of edge disjoint paths is always the minimum number of edges in an ST cut. Right? So that is this part here. Okay. So in this bottom chain of inequalities, the left one is just by definition of max, right? For any number of paths packed is less than max. And on the right side, the minimum number of edges cut is at most whatever cut you come up with. Okay. But what we've shown is what the algorithm will produce is a set of paths and a cut in the original graph such that the sizes are equal. Right? Okay. So we have this chain of equality, but the opposite sides are equal. What does that say about all the inequalities in the middle? Think of like a sandwich kind of. Oh, okay, we flattened it out. So they all have to be equal. So this is really strong, right? At some level, we've just gotten like a bunch of theorems all at once. Right? These are all equal. So first, let's look at points 2 and 3. Those are just comments about the algorithm. It returns a path packing that's optimum. And it returns an ST cut that's optimum. You get the right answer. But number 1 also is not obvious. It is not obvious that the optimums were going to be equal. Less than equal was obvious. And maybe in my examples, 2 was obviously equal to 2. But what we've really shown is that at some level, this maximum path packing from S to T and this minimum path covering from S to T, they're really two sides of the same coin. If you knew the value, if you knew the optimum value of one, you know the optimum value of the other. Okay, so at some level, you now also have an algorithm to get the minimum ST cut, which it probably would have been hard to think of even a good algorithm for ST cut. Somehow packing path, it seems more natural to try to pack path. At least you can think of the greedy algorithm. It's not so obvious even what's a reasonable idea to start with for a minimum ST cut. But it turns out it's so closely linked to maximum path packing and they solve each other simultaneously. This is very similar to kind of forests and spanning sets last time. It is duality. And the fact that the two problems together lets us solve them. Okay, but this problem is much more, I think, non-trivial compared to last class. Okay. All right. So the full algorithm, maybe at the end, if you also wanted to return the S to T cut, you would just run DFS from S in the residual graph and figure out the vertices S can still reach. Okay. And that'll give you an ST cut as well. Okay. All right, so great. As far as the running time goes, okay, finding a path is not so hard. That's like BFS or DFS. Okay. And rebuilding and adding the reverse is only going to take linear time. And if you're careful, you can kind of take that path you just selected and sort of walk backwards whenever you find an uncrossed path, sort of unzip it and zip it up with some other path you already have. And you just end up walking back to your original graph. So you can do this in OM time. You can also skip that step if you're only interested in the number of paths, or if you wanted to wait until the very end to sort of do all the uncrossing, so to speak. Okay. Yeah, so the whole thing takes linear time per iteration. Okay. And so usually the way people state it is they write m lambda, but lambda is just equal to opt, whatever is the maximum number of paths. Okay. Now, for us in a graph, opt is always at most m, right? Because each path uses at least one edge. So this will give you a polynomial time algorithm. You might think, oh, shouldn't it be less than or equal to n because S only has n edges leaving it? That would be true. But technically our discussion could have extended to cases where you have duplicates of the same edge, a multigraph, so to speak. So still unweighted, but you just have multiple copies of an edge. Okay, in which case opt could be m instead of n. So if it was a simple graph that promised no duplicates, then it would run in m times n at most. Lambda is at most n is number of vertices. But in a multigraph that maybe had duplicated edges, yeah, it could be bigger. Okay, but still polynomial time for this unweighted setting. Okay, that's it. I think that's what the theorem states. Okay. All right, so let me use the remaining time to frame and set up what we'll discuss next time, which is an extension of this problem. But sort of somehow this extension is very interesting. So, okay, we have mostly probably in our mind been imagining simple graphs with no copies of edges, but it could always have worked with copies of edges. Next time, we're going to introduce edge capacities. Okay? So you can think of them as like pipes and the width of pipes. Okay? So if an edge is labeled, I guess, 3 here, it's saying I'm allowed to use that edge up to 3 times. So you don't have to be edge disjoint anymore, just the number of times I use an edge among my path packing is at most the capacity of that edge. So it still follows this packing and covering framework, but sort of I'm allowed to reuse an edge multiple times. Okay? So here the solution would be, I think 5, because I can take one edge path down the middle, and then we can go across the top twice and through the bottom twice. Okay, so yeah, I've used, you can see I used the middle edge once and it's labeled 1, that's okay. I used the top left edge 3 times, but I'm allowed to use it 3 times. Okay, it's a very similar problem. Okay, at some level, if I give you integer capacities like this, you could turn it into a multigraph by, say, taking the edge that's labeled 3 and just making 3 copies effectively was labeled 1. Right? So I can duplicate edges and turn it into the kind of unweighted, uncapacitated setting. Okay? So at some level, we can solve this problem. In particular, all our theorems immediately hold. Those are math theorems, that the maximum number of edge disjoint paths is equal to the minimum cut. Right? But what are some issues that can arise? Yeah.
The weight of an edge is really big.
Those edge weights can get really big, right? In which case, sending one path at a time is bad. So your intuition works, but it won't give you a polynomial time algorithm, so we'll have to do something more clever. Another issue that comes up, besides being very large capacities, we can also think about like fractional values. What if the pipe allowed for 2.2 paths? Right? What does 0.2 of path mean? So we would want to extend our discussion to say a fractional path packing. So sort of like a weighted combination. I want 0.3 units of this path, 0.4 units of that path, 1.5 units of that path. So that for any edge, the total kind of quantity of path used in the edge is at most the capacity of the edge. Okay? But this also kind of breaks our sort of induction. I mean, before we had a counting argument, right? Like one less edge, one less path, one more path, one less edge, one more path, one less edge. Now if it's like, 0.2 more paths and 0.2 less edges, but if that 0.2 gets smaller and smaller, it's not clear that we're going to kind of really finish off our argument. In fact, there's weird examples where you use like irrational numbers and it just goes on forever. Okay, so we'll have to figure out how to deal with that. Although at some level, even if they were fractional values, but I told you they were all rational values, so 3 over 7, 11 over 17. How could I use what we've done today and get a slow, but nonetheless an algorithm that gives me ultimately a fractional packing? Yeah?
Find the, whatever you have to multiply by to get.
We can clear denominators. So if it's rational numbers, so a over b, I can multiply all the b's together or find even a better kind of more compact b, multiply that out, what's left is integers, very large integers. But we can, at some level, get a correct but slow algorithm for the integer case. That will give me an integral path packing. And then I divide that down by the denominator I cleared out by. So at some level, everything's okay for rational numbers except for running time issues. Okay, but the math theorem is okay. Now, as far as the math theorems go for weird irrational values, where you can't just clear denominators, and you want to know if max is equal to min, you can always still show max is less than equal to min, but the question is whether it's equal. But you can always take your rational values and get very, very similar rational values. Right? You get arbitrarily close, but rational. So instead of writing pi, you write 3.14. And then you add another digit, another digit, another digit, right? So you can always get that max is less than equal to min plus small number. Or small number is under your, or max is greater than min minus small number. Or small number is under your control, and then you gradually just take the limit as small number goes to 0. So the point being, this doesn't help you algorithmically, but as far as kind of whether the maximum kind of quantity of paths you can pack, even when the numbers are all screwed up, is equal to the minimum total cost of the edges that in a cut, they're actually still equal because you can kind of approximate and reduce to the integer case. So the issue is really algorithmic. The math is kind of laid out. Okay? All right, that's it. Thank you.